mean value theorem question. If you look at what it wants, it actually wants to know which slope will my derivative equal using MVT. Remember, MVT only applies when a function is continuous and differentiable on an interval. So we need to be continuous on the closed, differentiable on the open. Because this is a polynomial, that would be the case. So I can right off the bat get the average rate of change if I take f of 3 and subtract f of 1. There's my change in the outputs. And then if I do 3 minus 1, I get my change in the inputs. This is 26 over 2. I'm plugging the 3 in here, get 27. Plug the 1 in here and get 1. So 26 over 2 is 13. Now that is the answer to this question, but typically what we would do is we would take the derivative of the function. That's the derivative of the function, and we would set it equal to that average rate of change. And then I would finish this problem by determining what x value is inside this interval. And obviously there would possibly, I would think, be one, it would be the square root of 13 over 3. But for this specific question, this is what we need. For the second question, we are trying to find an absolute value, absolute max. An absolute max requires us to make a t-chart of coordinates. And the t-chart consists of the endpoints, but it also consists of critical values. The critical values are when your derivative is 0 or undefined. So if I take the derivative of the original function, I get this. If I set this equal to 0 and factor, I can take out a 3 and be left with x minus 2. So I have two potential critical spots where I could have an absolute max. Now this is a cubic, right? So a cubic is going to behave on the f of x graph like this. And it's a closed interval, so we just don't know quite yet, you know, where is that box, where is that window going to be represented. We don't know that quite yet, so let's do some more digging. We're going to plug these values into our original function so that I can get my output. So negative 2 goes in, we end up with negative 8. This would be minus 12 plus 12, that would be negative 8. 4 goes in, we'd have 64 minus 48 plus 12, that would be 28. Plug in 0, we end up with 12. And we plug in 2 and we end up with 8 minus 12 is negative 4 plus 12 is positive 8. So the winner here would be 4. Down here, we're looking at relative extrema. Relative extrema would come from critical values in the first derivative. So we're going to take the first derivative of g and get 4x cubed plus 12x squared. That will never be undefined, it will only equal 0. So let's see how many solutions we would have. If I take out a 4x squared, I am left with x plus 3. And that only actually gives me 2 x coordinates. And that would be 0 and negative 3. So that's 2 critical values, potentially 2 relative extrema. The only way to actually figure out if the critical values are extrema is to use a number line. So I'm going to put -3 here and 0 here. I'm going to plug these values into the f prime function, which is going to be right there. So let's start with a number way over here. Number way over here would be 1. That's a positive and a positive. This is increase. A number in here would be -1. That'd be -4, positive 12. That's still increase. And then if I plug in -4, that's going to end up being negative. That's decrease. So I technically only have one extrema, and it's at -3. The last one on this front page is talking about concavity. I have a function that is sine of x plus cosine of x. I'm on a closed interval since it's trigonometry. That's common. We want to know the x-coordinates of the point of inflection. And I only want it where concave down turns into concave up. So let's go ahead and derive this function twice. If I derive this twice, right, sine would turn into cosine, cosine would turn into negative sine. This is the second derivative of the first term. If I derive the second term twice, it'd go negative sine, and then negative sine turns into negative cosine. So I want to figure out where my second derivative equals 0. These would be all my potential points of inflection. If I move the sine of x over to the other side, I want to figure out where sine of x is equal to the opposite of cosine of x. When is sine of x equal to the opposite of cosine of x? So let's think of the unit circle. I want sine and cosine to be opposite and equal. That would happen in the second quadrant right here at 3 pi over 4, and that would happen down here in the fourth quadrant at 7 pi over 4. So here's your 7 pi over 4, and here's your 3 pi over 4. Now, these numbers are just, all those are the critical values of the second derivative. So I'm going to put 3 pi over 4 here. Oops. Now I'm going to put 7 pi over 4 here. And remember, since this is operating from the unit circle, I'm going to close these arrows into a fixed space. So that's 2 pi. And this is a 0. Let's test some values. The test values are going to go into the second derivative. Okay, so I want to know where concave down turns into concave up. So let's start with plugging in, I don't know, let's say pi over 4. Pi over 4 actually probably be a little bit more complicated to do. So let's just go with pi over 2. Pi over 2 is in that realm. So this would be positive 1, but the minus would make it negative. So that's -1. Minus 0, this is negative, this is concave down. Okay. Between these we have pi, let's test pi. Negative sine of pi is 0, minus cosine of pi is a double negative, this is concave up. A plug in would have to be kind of in this region. That's not a lot of, flexibility, so I'm going to go with 11 pi over 6. 11 pi over 6, if I plug that in, sine is negative, so a double negative would be positive. And if it's 11 pi over 6, that's actually -1/2 for sine. So right now I'm just going to keep track of this. Positive 1/2 with the double negative. I'm going to minus a positive √3 over 2. That's going to be a concave down victory. So I got 2 points of inflection. The one that I want to pay attention to is that one. So that's A. Question, we have an F prime graph and it wants us to analyze it and check for true statements. So let's start with this. It says F is continuous on the open interval. So starting this way and coming this way, are we continuous? And that's easy. Since this is F prime, that shows outputs for derivatives. If you have a derivative, you are alive. You are continuous. This is true because it shows differentiability. The second, you're decreasing on the open interval a to b. That is false because if we are looking at f prime, all of these coordinates are showing negative f prime, which is decreasing. But up here we have increasing. So because of all this, that's false. Last but not least, we are looking at the graph being concave down on the open interval. Concave down on an f prime graph means negative slopes. So if I'm checking for negative slopes, that is definitely true. I have negative slopes this entire time. I'm going downhill the entire time. So that would be true, and this answer would be 1 and 3. On this question, we have the f double prime graph. Our job is to actually get f. We've never had to do that. So the thing is, we're going to have to use f double prime to analyze concavity and points of inflection. That's the best we can do. So take a look. I've got a point of inflection here, and I know that because my concavity is positive up here, but then all of a sudden it turns into concave down right here. Negative outputs. Now it's going to stay concave down all the way to there, and then right around this dot, that is a second POI, and now I turn into concave up again. So concave down, POI, concave up, POI, concave down, POI, concave up. So let me draw that. We got concave up, POI, concave down, POI, concave up. There's only one that looks like that, and it's D. Last one is an optimization problem. We have a cylinder. The volume of this cylinder is 16 pi. So I can already write one of my equations, my primary equation, you could call it. And that would be pi r squared times h. My secondary equation is the one I'm trying to either maximize or minimize. And it says we want to minimize how much product we're using. So that's a surface area question. So I'm going to go with surface area, and because it's a cylinder, that formula would be 2 pi r squared plus the label 2 pi rh. I'm going to go ahead and solve this equation for h. If I do that, the 16 will remain in the numerator, the pi will cancel, and the r squared will go on the bottom. So when I sub this in for h, I'm going to end up with a surface area formula of 2 pi r squared plus, instead of 2 pi rh, it will be 32, because it's 2 times 16, pi, and then that r will cancel with one of these r's on the bottom, and I have that. So there's my surface area equation. If I am doing this question without a calculator, I'm going to go ahead and differentiate first. So we're going to end up with, we want the derivative to be 0. This would be 4 pi r minus 32 pi over r squared. From there, no calculator, I'd put the 32 pi over r squared on one side. I'd put the 4 pi r on the other, and I would just treat this like a cross multiplication problem. And I would get 4 pi r 4 pi r cubed equals 32 pi. The 4 and the 32 reduce to 8. The pi's knock each other out, and so I get r cubed equals 8, and that works out really well. My radius of this cylinder to minimize is 2. If the radius is 2, I can go back and re-substitute for my h. So 16 over 2 squared is 16 over 4. So this cylinder's minimization will require a radius of 2 and a height of 4. So here's my answer.